Hello everyone, I will be presenting our paper on leap submission for the third DIHARD Diarization challenge. This is the outline of the presentation. I will begin with the introduction where I will discuss the key contribution of our work. Then I will describe our leap system, which includes narrowband-wideband classifier, wideband system, narrowband system, followed by experiments and results, and I will end with the conclusion. Let's begin with the introduction. The third DIHARD challenge involved the task of partitioning the input audio stream into segments based on speaker sources, which is called as speaker diarization in challenging condition. The dataset comprises of a mix of narrowband and wideband speech recordings from 9 to 11 domains with 1 to 10 speakers in each recording. There is up to 80% overlapping speech in the dataset, and around 24% of the recordings are narrowband with 2 speakers per recording. There are 2 tracks in the challenge, track 1 which provide ground truth speech activity region and track 2 which does not provide the ground truth set. This slide shows the highlights of leaf system for DIHARD 3. We proposed a band classifier which classifies recording based on bandwidth, narrowband versus wideband. For narrowband, we used an end-to-end system, and for wideband, we used an X-vector-based PIC system. We explored different X-vector architectures. We also replaced the traditional AHC with the path integral clustering, which is a more robust graph-based clustering algorithm. In this section, I will discuss the leap system and different blocks in that. This is the overall block diagram where we feed the input audio to the narrowband-wideband classifier. If the classifier predicts the recording as narrowband, we pass it to a narrowband end-to-end system shown on the left side. And if the classifier predicts it as wideband, we pass it to a wideband PIC system, which is shown on the right side. Details of which will be covered in the next slides. The narrowband-wideband classifier is a simple 2-layered neural network, which is trained using the X vectors extracted from 7-layered TDNN network. For evaluation, we use 10-second segments segments from a recording with 5-second shift, and the 5 12-dimensional features are fed into the network. The output for each segment gives classifies it into narrowband or wideband. For the entire file, we use the majority voting to decide the bandwidth of the file. This block diagram shows the narrowband system. The architecture is inspired by EEND model with the encoder-decoder based attractor calculation. Input is 23-dimensional long Mel filter bank with a temporal context of ±7 frames. The model uses 4 transformer encoder blocks with 4 attention heads, and the model is trained with permutation invariant loss. This is the block diagram for wideband system. We use the multi-stage baseline setup in which we explored different X-vector architecture, extended TDNN and factorized TDNN. The output of the network is 5 12-dimensional X-vector, which are fed to the path integral clustering or PIC algorithm, where the encoding space is captured by a graph, and X-vectors are the nodes of the graph connected by edges. The weighted adjacency metric is computed using similarity score. The output of PIC is then fed to the VBHMM module for further refinement. We also added a binode.audio overlap detection module to detect the overlapping regions, and then based on that, we produce the diarization output. This table shows the differences in the architecture of ETDNN and FTDNN. Both the architecture have 14 layers, but ETDNN has 22 frames temporal context, whereas FTDNN has 32 frames temporal context. FTDNN replaced the pre-pooling layer by a factorized TDNN, which reduces the computational complexity as it represents the weight matrix as a product of two low-rank matrices. The 12th layer 512 dimensional affine output are the extractors for both the architectures. In our setup, we use path integral clustering, which is a graph-based agglomerative clustering algorithm. It exploits the connectivity of directed graph to cluster the embeddings in the graph space. Given a set of extractor x1 to xn, we create a directed graph G, where V is the set of vertices corresponding to the samples in X, and E is the set of edges connecting the vertices. Then we compute the adjacency matrix using similarity score. It computes the incremental path integral, which is the sum of all possible paths of all possible length between the cluster. And clusters with maximum incremental path integral get merged iteratively. This slide highlights the computation of affinity between two clusters in PIC. Cluster A is shown in orange color and cluster B is shown in the blue color. And we compute incremental paths in cluster A, which is all possible paths starting and ending in cluster A going through cluster B. And similarly, we compute incremental paths in cluster B, and the sum of the paths weights of these two terms is the affinity between CA and CB. And the cluster pair with highest affinity gets merged first, and then we recompute the affinity for the next merging process iteratively. This section, I will discuss the experiments and different results we obtain on the DIHARD set before DIHARD evaluation and after DIHARD evaluations. For training the X-vector extractor, we used Voxelab 1 and Voxelab 2 datasets with 7,323 speakers. For EEND training, we simulated 100,000 two-speaker mixture from switchboard cellular and NIST SRE dataset trained for 100 epochs. Finally, we adapted the model on call-home subset containing two speaker files. For evaluation, in the wideband system, we extracted 1.5 second X-vector with 0.25 second shift. We used cosine score as well as PLD scores for clustering, and we implemented path integral clustering, where the number of speakers is generated using the PLD plus AHC threshold fine-tuned over the dev set. For narrowband system, we downsample the audio to 8 kHz. And then subsample the frame level features by different factors, and we predicted at least one speaker based on maximum posterior probability each frame, and discarded the silence frame using the grounded SAD for track 1 and the baseline SAD available for track 2. After the DIHARD evaluation, we trained another EEND system for wideband domains, which is trained using Voxelab 1 and Voxelab 2 and Debrissage dataset, which contain up to 4 speaker simulated mixtures. We also performed comparison with the VBX system. These are the results for track 1 dev set. For comparison purpose, we have freezed in the table the X-vector model as a TDNN, and we performed experiments with PLDA plus AHC, PLDA plus PIC, and cosine plus PIC setup, and we found the best performance is obtained with PLDA plus PIC. We also compared our approach combined with VB and overlap detection, and we found that we are getting around 3% improvement over the baseline with VB, which is finally used in our final submission. For narrowband, since the number of speakers are 2, we have computed the baseline by freezing the number of speaker 2, and similarly we have freezed the speakers in EEND module, and we can see from the table that there is a around 50% improvement in DER and a significant improvement in JER using the EEND model. This is the comparison of the performance of AHC versus PIC for each of the domain. There are 10 domains, out of which 9 domains are showing improvement over the AHC, where PLD plus AHC is represented in blue color and PLD plus PIC is represented in orange color. The RT04 has shown degradation in performance in terms of average GER, as it is a restaurant domain which contains a lot of short speaker turns, background noise, and overlapping speech, which has resulted in suboptimal performance, whereas the rest are performing better. These are the results for track 1 and track 2 in terms of diarization error rate. We are comparing our systems with the ETDNN and FTDNN architecture 1 and 2 respectively, with the baseline represented in blue color. We are getting 24% relative improvement in track 1 and 18% relative improvement in track 2 for the eval set in the DIHARD challenge. These tables show the post-DIHARD results. The first row is our leap eval submission for full set and core subset, which is the subset of full containing equal duration of audio in each domain. And then the second entry in the table is the VPX for wideband with overlap, and we have reached the narrowband system for our all the comparisons. So we are getting around 12.87 DER compared to 14.34 DER for the dev, and 14.53 DER compared to 14.88 DER in the eval set. So we can see the VPX, since it is tuned on the dev set, we are getting significant improvement in the dev, but for the eval that is not clearly reflected. But in the core set, we are seeing there is a improvement from 18.07 to 17.45, and there is also a 2% improvement in JER. Then we also tried initializing VPX with PIC, and we are getting slightly better results in dev, but the eval results are poor than our eval submission. We also the last row shows the EEND results, which produces suboptimal results because the model has not seen more than 4 speakers, so it fails to predict the higher number of speakers. I would like to conclude by saying that we proposed a combination of narrowband and wideband diarization system. The end-to-end system is found to perform better for 2-speaker narrowband recording. We improved the baseline for wideband using better speaker space embedding and novel path integral clustering scheme. We got 24% and 18% relative improvement for both track 1 and 2 respectively. In the post-evaluation analysis, we found that EEND system trained for up to 4 speakers is suboptimal for wideband system. VBX with AHC initialization shows best performance compared to VBX with PIC. This work is supported by the grants from British Telecom Research Center, and we would also like to thank Hitachi or DIHARD team for providing treated ETDN model for post-DIHARD analysis. Thank you.